Hello everyone and welcome to yet another recreational programming session with Mr. Azozin. So Python has a very interesting concept which is called generators. So it's kind of like iterators, but they also kind of not, right? So I'm specifically interested about this functionality which allows you to write function in sort of like imperative style, and then through a yield, you can kind of like yield more values and generate values. Right, so we can even take a look at that. So let me actually maybe create a folder like a Python generators. Right, so this is Python generators. I'm gonna open Python. Chat, look, I'm programming in Python. Isn't that cool? Right, so the last time I've been programming in Python, like I had a lot of views because people suddenly could understand what the fuck I'm doing. Right, so are you guys excited? Are you guys excited that I'm programming in Python so everyone can understand what the fuck I'm doing? Isn't that amazing? I think it's fucking amazing. So anyways, right, so let's actually maybe copy paste this entire thing. But maybe we don't even have to copy paste it, right? So we can say, yeah, so it's basically like generates first n values. But maybe we can, yeah, so let's generate first n values. And essentially, we need some sort of an iterator, right? So it's going to be like 0. And while I is less than n, what we're going to be doing, we're going to be yielding that I, and then incrementing that I by 1. So that's basically a generator, if I understand correctly. So I want to maybe make this entire thing executable, and let's actually do something like that. Okay, so and it didn't do anything, right? So it just worked out. If I now try to call this function, if I understand correctly, nothing really is going to happen. And I'm really curious what's going to happen if I try to print this entire thing. So calling this function created a generator. Right, calling this function created a generator, and then I suppose what I can try to do, I can try to maybe turn it into a list, and there we go. So here is the list. So essentially, this function kind of describes an object, and that object, if I'm not mistaken, right, so we can put it somewhere here. So this is going to be G. And this object has some interesting methods. Maybe we can even do something like dir. Right, so we probably have to do print to be able to see this kind of stuff. It has a method, yeah, it has a method next. Right, it has a method next. And then if I do something like G next, it is going to like pull one element out of this function, right? So it's going to execute this function up until one yield, and then return the execution. And then we can pull it again, and we can pull it as many times as we want, right? And it's going to do that, like basically continue the execution of the function up until the yield and return the value. So I wonder what's going to happen if I just like provide a very small value and I try to pull a thing when the generator is kind of finished. Right, so let's actually see. Oh, this one is kind of interesting. So it throws an exception stop iteration. It's kind of interesting. I didn't know that. Like I don't never really used like generators in Python that actively. I don't really use Python that actively as well. So I didn't know that it's going to throw an exception. I suppose when you do something like a list, J, the way list knows to stop is by catching the stop iteration exception. Bro, using exceptions for control flow, Python developers. And then you are like wonder why your language is slow. Anyway, so just a random thought. So, and it's kind of doesn't that remind you something? Doesn't that remind you something? The way how it works, you're gonna execute the function, and then you suspend the execution, and then you continue. Doesn't that remind you something? It's just like it reminds me something that we did quite recently, and specifically it's coroutines, right? So we kind of did a very similar thing with C, but not exactly the same. Here's the thing: it's kind of a similar, but not the same. And this is the reason why I'm streaming right now, because otherwise I wouldn't be streaming. Right. So let's actually take a look at that. I'm going to go to Sorting, coroutines, and maybe do I need to fetch the latest things? Maybe I did some changes to this framework, to this library, and of course the link to this library is going to be in the description. And for people in the chat, of course, you can do some sort of like a today command, so the link should be there. Okay. So we have a bunch of examples in here, and specifically the example that I have in here is counter. Right. So essentially, there is an operation go which accepts a function and a parameter for the function, right? So here's the function that accepts parameter. And then here, as you can see, it just performs the loop, kind of a similar loop that we had in Python, but then it calls yield, right? And we create several of such routines. Right, we create several of such routines. If we just create several of such routines and don't do anything, the program is not going to do anything. Right, so let's actually rebuild like the whole thing. And I'm going to do build a counter. Right, as you can see, the program doesn't do anything. But if I start doing yield, right, if I start doing yield, I probably need to do something like this. Yeah, there we go. As you can see, the coroutines start counting, right? And one coroutine counts through from 0 to 5 and another one from 0 to 10. And up until 5, they're kind of interleaved, so they duplicate values. And then the first coroutine dies and the last one continues counting up until 10. Right, so there's also a little bit of a suspension of the execution and then resuming going on in here. Right, but it's kind of different. So the main difference in here is that in Python, you can return a value out of the generator. Right, you return the value out of the generator. Here, you just call yield. And this is the main difference. When you call yield, what it does, it just switches the execution to the next existing coroutine. Not returning to the caller of the next, right? Not the caller of the next, but to the next executing coroutine, and it rounds robin between them. You can't really return values out of them. You can only switch to the next one. And usually, when you want to pass information from one coroutine to another one in this kind of setup, you have to use global variables and stuff like that. Right. So, and I was thinking, how can you implement something like that but in C? How can you do that? Like, you have to return a value. And I think we can use literally the same approach. We can use literally the same approach. So essentially how we implement coroutines in here, when you create a new coroutine, we literally allocate a stack, a new call stack, a second call stack, right? And when you switch the execution to the next coroutine, we literally on the level of assembly, switch up the stack. So we even have a little bit of assembly going on. If I find the correct source, yeah, there we go. So this is basically what we do, right? When you do yield, we save in the state on the stack, and then we switching up the context. If only Emacs cooperates a little bit. Switching the context. So this is where we're restoring the context, and as we're restoring the context, we're literally replacing RSP register on x86-64. We're switching up the stacks, literally. And that stack kind of preserves the entire execution context of the program, right? And you have several of such things, and you can on demand switch up the execution environment. So that's how it works. So if we want to implement these kind of generators like in Python, that object, right? So you call this function and it returns your object. That object could be basically the stack itself. And then when you call next, you basically resume its execution up until the next yield. And yield somehow should then return back to the calling of the next, and it should put the value it returns into the rax register. And rax register, according to the Linux x86-64 call convention, is the register through which you return the value. That way, you can kind of simulate these Python-style generators with yields that return the value on C as well, using the same kind of technology that we developed in coroutines, right? Right now, whatever coroutines we developed in here don't really do exactly the thing that Python does, right? Because they are incapable of returning anything. But if you employ the trick with the rack register, I think you can make it work like that. And it's literally going to be like this, right? So you call the function, it creates an object with its own execution environment. You then call next on that object, it resumes the execution environment, like gives you the next value, and you just like continue and stuff like that. I kind of want to try that, right? So because we already have the technology of capturing the environment, right? Capturing the environment and then switching the environment, right? So it's already there, right? It only needs an ability to return things out of that environment back to the original one, right? So we need to do something like that. Yeah, get context, set context. People keep mentioning get context and set context, but first of all, get context and set context are literally deprecated, aren't they? Right, so I heard that they're literally deprecated, and the question is, do they allocate a new stack? They do allocate a stack. Okay, so what I heard is that a lot of bad things about them. They're deprecated. They're not cross-platform and some yada 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 whatever. So it's better not to use them. Here we have our own thing that we fully control. You know what I mean? It's just like yeah, and we fully understand it, by the way, right? So because we literally wrote assembly for this entire thing, right? So we kind of internalize this entire stuff. So yeah, we got some subs and beats. Beats. So where do I start? So IB Talks, thank you so much for trying with the message. 2 years on board today. Congratulations, right? So thank you so much for trying. Lamexis, thank you so. I hope I pronounce Lamexis. I hope I pronounce your nickname correctly. Thank you so much for trying with the message. Python is unreadable after second indent. You're welcome. So Timar Tiro, thank you so much for 100 bits with the message. Which coroutine lasts the longest? I really know. So I should try them all, and as I try them all, I'll tell you. So Sandy X, thank you so much for 41 with the message. Oh boy, Python. Yeah, Python. Yeah. All right, so let me actually see what we can do about all of that. So it's kind of interesting, isn't it, chat? I think it's kind of freaking interesting. Let me see. So the way coroutines work right now is that when you do coroutine go, right? You do coroutine go. You provide a function that you want to execute. Right, in our case, with the generator, we're also going to provide that, and it doesn't really return you anything, right? And what it does, it allocates a new context object in a global array, and then the unique identifier to that object is the index in that array. So what I just realized is that you don't have to use indices in here, right? So here is the context, and context only contains the pointer to the RSP to the top of the stack and the pointer to the stack base, so then you can maybe deallocate it or find the top of the stack or something like that. So some sort of like a stable point relative to which you can find things, because RSP is a thing that is constantly moving. So what if instead of doing indices, we could have allocated that context, like this entire structure, on the heap. We could have allocated on a heap and use the pointer to this structure allocated on a heap as like an object, as the generator object. So we get a raid from T2SDE. Thank you so much. Thank you so much for the raid. Thank you. How was your stream? I hope it was well. I hope it went well. Hello. Welcome. Yeah, so, and it's kind of like, I just don't know why I didn't realize that instead of like doing this global array of things, I could have just like, yeah, just like allocate it on a heap and return a pointer to that, and that's your identifier. And then you can pass it to switch to it, and effectively you can just dereference that pointer, and it contains all the necessary information for you to do things. Right. So I'm thinking how I want to actually approach that. Do I want to embed that into the library, or do I want to create like a separate maybe project separate library. Let's actually create a separate folder where we can experiment with these things. Right, so Python, so I had a probe, right, so, and that probe is a Python generator. So, okay, so let's actually create generator .c, right. So we're going to have a little bit of a generators in here. So we're going to start from scratch, so I'm not sort of burdened by the complexity of the existing library, right? So I can kind of start from scratch, from fresh, right? And then if we come up with something interesting, we can then sort of take whatever we discovered and port it back into the library if it is portable, because I don't know if it is, right? So just like I want to experiment, I want to explore things, right? I want to reinvent the wheel a little bit. Unburdened by what has been, yeah, exactly, right. So because the more code you write for the system, the more it kind of constrains you, right? The more it constrains you. So if you want to like explore things in a constrained manner, it kind of better to start from scratch. What's up, Beijing? What's up, Beijing? So I already said that before. I think on Discord is that one day I want to visit Beijing. So then I can say loudly, "What's up, Beijing?" Because as far as I know, like in Mandarin, it literally means "I'm in Beijing," right? So which is kind of fun. So just like visit Beijing for the sole purpose of saying "What's up, Beijing," which in Mandarin means "I'm in Beijing." It's so good. I really like that. So anyway, we need to grab the context. So let's go to coroutine.c. Where is it? It's not counter. I wanted to find the context. Coroutine. There we go. So let's literally grab the context. And the thing I want to do, right, is basically have some sort of function generator create. And it's going to literally return you a context. Since we're doing generators, why not just call this entire thing generator? Yo, that's pretty poggers, meine Freunde. Let's just fucking call them generators. Right, so and in here, we're gonna just like accept the pointer to the function, which may accept some parameters, and here is the parameter that we can pass in there. So, you know, the usual shit. Right, the usual shit. So, and this time, unlike the coroutine Go, instead of creating an entry in the global array, we're gonna just do a malloc. We're gonna just allocate size of generator on the, you know, on the heap using malloc and stuff. So I already have std. Ayo, let's do stdlib. Right, so and in here we're gonna create generator g. Like this, and of course I want to kind of assert that this thing is not equal to null, because otherwise if it is equal to null, that means you don't have enough RAM. Just buy more RAM as usual, buy more RAM. Stop being poor, stop being poor. So, and after that, we just return that. And there we go, here's our generator. So we might as well even maybe create some sort of a thing in here. Okay, I'm kind of done with the counters, right? So we use counters like over and over again. It's kind of stupid. And let's actually create something else. Like what kind of other interesting generators we can come up with, chat. Maybe Fibonacci or something. So yeah, so let's actually do Fibonacci. Prime, yeah, maybe prime numbers as well. So Fibonacci. So let's start with the fib. Right, so this one is going to accept some argument, but we're not gonna even bother with that argument. Right, so so we need A and B, right? So this is the first one, this is the second one, and while we can use this as a limit for the Fibonacci numbers, right? So let's actually say something like max. Which is, we're gonna just literally cast that to integer, right? So the cool thing about accepting a generic argument as a void star is that if the argument that you want to pass is primitive, it will probably fit into the type of a pointer, right? So like integer or float or anything, just literally cast, reinterpret the bits of the primitive value that you want to pass as a pointer and then reinterpret them back inside of this function. And if it's bigger than the primitive type, you can allocate it on a heap and just, you know, pass a pointer, right? So it's kind of like, this is how we do generic things in C, right? So, and in this case, if we're going to be passing the limit for the Fibonacci, it's better like literally reinterpret integer as the pointer and just like pass it as it is. So, and this is exactly what we're doing. So then I can say, okay, so while while this thing is less than the maximum, the ceiling of what we're generating, what we're going to be doing, we probably want to yield this value, right? So, but we don't have a yield operation, so we'll probably need something like a generate yield. So when it's going to accept one of the, yeah, again, we kind of don't have any type information in here, do we? We kind of don't have any type information. And that's kind of sad, isn't it? We have generics at home, exactly. So yeah, it would be kind of cool if I could say like a template. So the type information of what the generator sort of like generates would have been associated with this thing, so that I could do something like this or whatever. Right, that would be kind of cool, right? So it's just like on top of having the generator store this entire thing, I also had like a type information. That would have been kind of cool. All right, so, but I can't do that in C. So maybe we should switch to a higher level language, maybe something like C++, or maybe something like Jai, right? Something like Jai. Do we have anybody from Kazakhstan in chat? Do we have anybody from Kazakhstan in chat? So recently I actually learned a revolutionary information. Yes, exactly. In Kazakh language, there's a word zhai, which means simple. I swear to God, I know that John is a huge fan of Borat. This must be a fucking Borat reference. Like, it must be fucking it. So, we figured it out. The name of Jai is coming from Kazakh language. Because it fits. He's a fan of Borat in Kazakh language. It means simple, and he's all about simplicity. It must be fucking... We figured it... We cracked the code. We fucking cracked the code. Yes. He's been exposed. Anyways, so let's continue. So, and by the way, in Jai, you can actually store this like extra information at compile time because there are generics in Jai. We can even take a look at some examples of the generics in Jai. So modules and a hash. Is that? No, it is not. I think it's something like hash table. So it has the most based syntax for generics, right? So essentially, it's a struct, but struct can be a function. Look at the amount of parameters hash table has. Holy shit. Yeah, so this is how you do generics in Jai. I'm not even fucking joking. So it has like a syntax of a function, and then if you want to like create a variable of this entire thing, you literally provide like a key type, like an integer, and value type, like an integer, and it also has like a hash function. So compare functions, some different, configuration for the hash table, and so on and so forth. Majority of them have default parameters, so you only have to provide the key and value. But if you want to customize some of them, you can actually do that. And all of that are template parameters. So, and you can pass function as a template parameters, and all of that is a compile time thing. And you don't even have to provide like them in order, because you can have named arguments. You can only provide the compare function if you want to, right? So it works like that. So, and it preserves this information at compile time. So it's pretty cool. It's pretty cool. Right. So. Oh, and it also has like a for expansion for the for each loops and stuff like that. and stuff like that, and stuff like that. All right. Anyway, but we're not gonna do gyre right now, but maybe later we can try to do that. By the way, when you're doing generator yield, right? When you're doing generator yield, you also need to kind of know what generator you're dealing with right now, right? So that means yield probably has to accept the generator as the first parameter in here, doesn't it? Right, because it needs to know what kind of generator it's dealing with, because it needs to then return back to whoever called this entire thing. But we don't have the generator in here. When I do generator yield, like I don't have the generator in here. Chat. So I suppose maybe one of the things we have to do in here is pass the generator as a parameter. So that means the signature of that function, that can be a generator, has to be like this, right? It has to be like this. So, and then when you do generator create, you have to pass these sort of like parameters, you know, through the registers or something like that. Like you have to do it. Right, and by the way, this entire thing should probably actually cast to void star, right? So because the yield accepts the void star. Right, and I suppose the generator also should store the information about like where to return from who called this entire thing. Yeah, so for now, I'm going to keep this entire thing and implement it, right? So I'm going to do to do, right? So this is going to be yield. And this is how we're working with all of that stuff in here. So, okay, so after that, we need to compute the next Fibonacci number, right? So I'm going to do maybe something like C, A plus B, A becomes B, and B becomes C. Right, and we just continue. And as you do yield, it kind of suspends the execution, returns to whoever called next. And by the way, we need some sort of a generator next. Right, so that means we'll need to have something like generator next. And we'll probably need to accept just a generator in here. And we're going to actually accept, like, return the value that was passed into the yield. Yeah, so right now this entire thing obviously is not implemented, right? So it is not implemented. So let's actually put this kind of stuff in here. All right, that's pretty cool. So, and how I envision the usage, by the way, this thing is also not implemented, right? So I just kind of designing an API, just like trying to figure out all these things that I need. Right, what I have to do generate create. I provide the Fibonacci thingy, and I'm gonna say, okay, so generate like million, up to the million, right? So Fibonacci sequence grows pretty fast, so it's gonna exhaust 1 million very quickly, so it's not gonna be too much, right? So I can take this entire thing and like literally cast it to void star, right? So, and that gives me a generator. Which I then can you know, poll by doing generator next, right? So I do G, and generator next should resume the execution either from the beginning if the generator was just created, or from the yield if it was suspended, right? So it should do the execution up until the next yield, and then whatever we passed in here should be returned from the generator next. And that is very much close to whatever we had in here, right? Because look, this one doesn't really call this function, it creates the new generator. So here is the G, and then we do next. We can even kind of, yeah, so we can kind of simulate the same code, right? So I called it 4 times in here, and then I can do maybe I can cast this entire thing to an integer, and let's do a little bit of a Emacs magic. So print f d like so, and boom. So now this code kind of looks like a Python, right? So we create the generator, and then we just like poll the next. And then we just poll the next. So generators can have return. I suppose doing return will instantly like exhaust the generator. So that means we also need to probably have some information about the generator being dead or whatnot. You know what I mean? So we need some information about the generator being dead. So because if you try to maybe do next on a dead generator, if G dead, we can just do abort, right? So throw an exception or something like that. Right. Because we need to know that. We need to know when to stop, but I'm not really sure because we need to be able to return the value, but then how do we know that, you know, the generator is dead already? So we need to return two values apparently, right? So we can maybe return like some sort of a structure, or we can return one of the values through the parameter in here or something like that. So I have not decided yet, but we'll see. So I need to compile this entire thing, right? So let's actually, I kind of been using makefiles lately instead of knob. I think I need to go back to my roots and find, like, use knob again, right? So I kind of abandoned knob as of late. Okay, so let's take a look at the subs. That's a lot of subs. Okay, so thank you so much, Sir Joyth III for tier 1 subscription. Howard Rourke 11, thank you so much for Twitch Prime. In Lois, thank you so much for Twitch Prime with the message double digit. Let's go, my friend. Desert Fish 2, thank you so much for Twitch Prime. Elliot 404, thank you so much for tier 1 with the message. Thank you for your awesome work, Mr. Zozin. You are welcome. You are welcome. I ran out of water. Okay, so where is my knob? Sodium 2025. Let's grab the knob. Let's grab the knob, a fresh knob. So here's row, and I'm gonna just, like, you know, download that with wget. All right. So here's this thing. So let's create knob.c. I'm going to include knob.h, and obviously I want to include implementation as well. Implementation and knob strip prefix. So let's create entry point, which is argc, argv, and then we're gonna do a magical knob go rebuild yourself technology. argc, argv, and I'm gonna just return 0 in here. Look at that, look at that. So if I do something like knob.c, all right, we bootstrap this entire thing, it doesn't do anything. So we are ready to start maybe, you know, building some things. So I'm gonna create a command, and let's append into the command some different things. For example, the compiler. So I'm going to enable all of the warnings and all of the extra warnings, maybe some debug information. We probably will need the debug information, right? So because we're doing like a low level thing, right? So, so do we want to be pedantic? I don't want to be pedantic today. So the output is going to be a generator, and the input is going to be generated.c. I also like to create like a build folder, so to not to pollute things, but we're probably going to have only a single executable, so maybe build folder is not needed right now. Okay, so we create the command. Now I need to run it. So to run the command, I think I'm going to use a synchronous run. So knob cmd run synchronously, right? So that's the thing I want to do, and I also want to reset the CMD. So additional reset just sets CMD to 0 again, so I can run several commands if I need to. So it just, like, you know, simplifies some things a little bit. So if this thing fails, I'm also going to return a non-zero exit code. Let me rerun this entire thing, and that didn't compile. Okay, so because we don't have a boolean in here. All right, so let's actually go to the compilation errors, right? So I need to include std_bool. Any other compilation errors? I don't have a to do. All right, so because to do is located within knob, right? So one of the things I can do, I can include knob not only in the build script, but also in the main application. So this is kind of a cool thing about the knob library, right? So you have the builder of your application and your application, and they both use the same library. That's kind of cool. This concept is kind of old already, right? So, but I still can't get over it, right? So, like, they kind of use the same sort of like base code. It's kind of cool, right? So, and then here we can just like include. Why can't I spell include? Thank you so much. Knob.h and define knob implementation, right? So, and also I want to probably strip the prefixes, otherwise I won't be able to just do to do strip prefix, right? So you have to strip prefixes, otherwise you kind of have to prefix everything with knob, which is a little bit annoying, but it's needed for, you know, namespacing, right? So because C doesn't have any namespaces or anything like that, so the names can just collide. But sometimes it's just too noisy. Because of that, we have a mechanism of stripping of the prefixes in case when you know for sure that nothing is going to collide. It's kind of a funny mechanism, like for literally for each individual name, we create an alias with define, right? So it's kind of funny, I think. But anyway, so that will allow me to just use to do as it is, which is rather convenient. All right, so what are you complaining about? Okay, so we have a bunch of unused things. I also have a special macro that allows me to mark something as unused. Right, so for the time being, until I implemented all of these functions, I'm gonna just mark them as unused. So it doesn't like, so void star is actually 64 bits and integer is 32 bits. So it's kind of dangerous to cast it like that, but can I just cast it to long int? Apparently I can. Okay, so that's pretty cool. So, and it cannot cast a shorter integer into this one. Can I just cast it to long int first? Oh, that's... So first we're casting it to a bigger integer, and only then we're casting it to a point. Can we just like... can we just use long instead of integers? Just use long then, if that's what you want to do. Right. So in that case, we probably don't even have to do it like that. Right. Anyways, so here we have f. Oh, it's unused right now because we haven't finished it. Okay, so let me actually mark it as unused. So this is that and RG. We're gonna use them at some point. Don't worry about that, chat. Okay, so in here, yeah, so we'll probably want to cast them to longs, right? Because they do return longs, and because of that, these things has to be LD. But we can actually let the compiler complain. Yeah, right, so there's a mismatch. So this is a long integer and this is an integer. Right, so the modern compilers can actually detect this kind of scheisse. And there we go. So it actually kind of worked. So obviously it's not going to work if we try to run the generator, right? So it's going to hit the first to do, right? So it hit the first to do in here. Who needs Rust? I have my own to do, right? So yeah, is that progress? Progress. C is all you need. In PTR, yeah, by the way, we could have just used in PTR, right? So because it's basically an integer of the size of the pointer of the platform. But to be fair, like, I mean, I'm on x86-64, right? And I don't really plan to mess with any other platforms right now, and I'm just experimenting, so it doesn't really matter, right? So we just need to use whatever works. Whatever works, what works. So anyway, so let's actually try to implement generator create. So the first thing I want to do, I want to maybe memset the entirety of this thing to 0, just basically 0 initialize this entire thing. Right, so and 0 initialize dead is going to be by default false, so that means the generator by default is not dead. All of these things are going to be zeros and stuff like that. So next, I probably need to copy paste the code in the coroutines, which does the stack allocation and stuff like that. So coroutine, what is it called? Go. Right. So this one is rather interesting. So you can learn about how we allocate the stack from my previous sessions. I think I'm going to put put the session in the description. Link to the session where we allocated the stack for coroutines. Yeah, so this thing basically. So we're using a map with different parameters optimal for the stack allocation. And I can just like do something like this. So, and in here, I'm basically doing that for J. So here's the stack base. Yeah, and it grows down and stuff like that. So yeah, we allocated this entire stuff. So we also kind of in here asserting that mmap didn't return a failed value. I think that's fair. I'm not really sure when mmap returned failed. So does it return failed for the same reason why malloc would return failed? Well, we can actually take a look at the documentation of a map. So when does it return failed? Right, so return a pointer. So this is the kind of different errors it may return. E-access, it's when you provide the file descriptors. mmap can memory map files. We don't really have files, so this error probably not applicable to us. E-again, the file has been locked or too much memory has been locked. Okay, so, well, I guess it may fail for the same reason as malloc, right? Not enough RAM, or yeah. So there's no mem when you you know, out of memory and stuff. That's a lot of reason, right? Jesus, it may fail for a lot of reasons. Anyways, so I don't know. I'm gonna just assume that yeah, it may not fail, right? So especially with these kind of parameters, because whatever. Anyways, so after that we are preparing the stack, right? So this one is rather interesting because after we prepare the stack, we have to push a lot of things on the stack, right? So we have to push a lot of things on this stack. So, and in here, yeah, we're gonna just do it like that. So this is RSP. And what do we push on the stack for the coroutines? Okay, so the sort of like the last thing that is going to be on the bottom of the stack is a return address to something that finishes the coroutine. But in case of a generator, what exactly do we even put in there? What exactly do we even put in there? Do we put something special? I don't even know what we put in there. We can put something that takes the current generator and marks it as dead, right? But then you have to pass that generator there, and the question is, how do you pass it in there? Because you probably have to pass it through RDI or something. Well, since it's a return address, you probably pass it through the racks, or if it's going to act like a call, you probably pass it through RDI. So there's a lot of like questions about how exactly you do that. Yeah, and having like a generator around is kind of a difficult issue, right? So because when we had just a global array of generators, it was not a problem because it's just a global array. But now a generator is a parameter. The currently running generator is a parameter. So the question is how we like work with that. Maybe we can make the generator a global variable, right? So maybe we can have a global variable that denotes here's the currently running generator, right? Push generator, pop generator. Yeah, kind of like that, right? So it's kind of similar to the context mechanisms of Jaya or something like that, but yeah, I'm not really sure. But my point is that when you do generator next, upon switching to that generator, it also sets some global variable, right? So current generator. So here's the current generator, which is by default null, right? So, right, when you're running in just like a current environment, current generator is null. When you do the next on a particular generator, you set the current generator to that, and because of that, maybe you don't even have to now pass this as a parameter anymore, and that kind of simplifies everything. Look at that. Is that a good idea? Right, so since we're going to be running like in a single-threaded environment, I think it's fine. And if it's going to be a multi-threaded environment, well, I mean, we have a thread local. You know what I'm talking about? I think this is a good idea. Right, so it's just like, because you're either running in the current in the non-generator environment, or you're running in the generator environment. Right, and it's kind of a global flag. What if the generator uses another generator? This is a good question, actually. So that means they have to, is that a stack of generators? Is that how Python works? Is that a stack of generators? This is a good one, actually. All right. Yeah, so, okay, so that must be a stack of generators. Kind of similar to how Jaya works. By the way, when Jaya does pushes, yes, a stack of okay. Sack of genitals. Anyways, so yeah, I think it has to be some sort of like a stack. It's a stack all the way down. Yeah, but we can always do something like a type def struct generator stack, right? So it's going to be generator, and since they're pointers, right? So it's going to be double pointer items, size t, count, and capacity, right? So the reason why I'm calling these things like that, so all of that is kind of compatible with the di append macro that everybody knows from Twitter. Because they see an assembly grifters keep reposting this entire video over and over again. Can anybody explain to me why grifters like that particular video so much? I don't fucking understand. Right, so what's so special about that fucking video? Anyway, whatever. Maybe we should make more videos in a similar style. But to be fair, I don't really know like what kind of topics can I explore. Ooh, maybe some string buffers. Maybe it performs well. Maybe it's engaging. So generator stack. So it's something like this. So this is going to be something like that. What the fuck is thread local? It's a keyword in modern C. Did you know? Did you not know? It's a famous keyword in C, thread local. I'm not even joking, it is a keyword, C, thread local keyword. So it is used to mark a variable with a thread storage duration, which means it is created when a thread starts and cleaned up when thread ends. Note for C, C++ or later is required to use the thread local keyword. So I suppose it is like, you know, separate per thread. Each thread has its own copy of that variable. Did I understand correctly? Right, so it's kind of needed for multi-threaded environment. Every few months I find something new feature in C. Exactly, that's the thing, right? So I already talked about it. C is insanely deceiving, right? It's a deceivingly simple language. In reality, you can keep learning this language your entire life, and there's always something new about this motherfucker. There's always something fucking new. To be fair, thread local keyword is a relatively new feature. I think it's like a C++ 23 or something. Like, when did they introduce that? I don't really know. We can take a look at that. So yes, it's a C23. I'm not gonna even use in C23, honestly. So maybe I should not use that. Oh. What am I supposed to use then? See, is thread local is itself a keyword which may also be so they removed macro because it became a key. Okay. Okay, so they didn't remove thread local, they just promoted it from a macro to a keyword. Got me scared a little bit. So thread local. I'm not really sure if I need this here, but whatever. So we're gonna have stacks in here and stuff like that. So generate the next. Generating God seed. Throw another run. Okay, good. And by the way, so now when I want to finalize the current generator, I can just get that information from a global stack. Bro, this global stack idea is best. So guys, it's generated the same as coroutine. I think you can use the same sort of underlying technology to implement both generators and coroutines, but technically they are different. So the coroutines that we implemented in C, they can't return values. The generators, like in Python, they can return values. So there's a little bit of a difference in here, so that's for sure. But anyways. So here is the stack. Okay, so we prepared the stack. So let's continue copy pasting the code chat. So in here we do coroutine finish current. So here I want to maybe do something similar, generator finish, yeah, finish current. Generator finish current. So what's that going to be? So it's going to be void. It's probably not going to accept anything. And for now, I'm going to just say this is not implemented, right? So just go ahead and implement that. Cool. So that's going to be at the bottom of the stack. So then we are going to put the function f in here. Where's the function f? Yeah, so here is the function f. The code is a little bit noisy, haven't you noticed? This is because of a word wrapping in here. So can I just toggle word wrap, or maybe toggle, so I think it was a line truncate. Yeah, toggle, yeah, there we go. So it's a little bit less noisy because this particular line doesn't wrap around and it just goes outside of the screen. Is that a good idea? It kind of makes it less noisy, but at the same time you're missing a little bit of a code. I don't know. So here is the function into which you're going to be jumping, and here is the argument that's going to be called with the function, and then the rest of the sort of state of the execution, various registers that usually preserve their the values between executions. So we kind of store all of that stuff. Right, and after that, we need to set the RSP of the generator to this thing, and that should be it. And then we just like return the generator, right? So we just allocated the generator, we initialized its execution environment, and then we just like returned that specific generator. Isn't that bogus? I think that's pretty freaking bogus. Right, so let me try to rebuild the whole thing. Right, so what does it say in here? Thread local. I need to include the threads. Right, so let's go ahead and just include the threads. Semicolon. Didn't spend 3 hours debugging, which is nice. G's, okay, so since we don't pass G anymore, we don't need that. A map. Okay, so this is a platform dependent shed. So what do we need to include to have an access to platform dependent shed? We have to include this thing. Okay, that's cool. So maybe I'm going to actually organize my includes like this. So here is the cross-platform stuff. This is the standard library, so it's cross-platform. This is a platform-dependent shed, and this is knob. Right. So this is like a custom third-party dependencies. Right, so this is how I'm going to organize my includes. Stack capacity. Okay, so this one is interesting. So generator stack capacity. So how big of a stack we want to have by default? Also 20 megabytes. So what do we use in the coroutines? I think... yeah, oh, actually 1 megabyte. So we take the size of the page. So we allocate 1024 pages, right? So it's basically 4 megabytes because the size of a page is 4 kilobytes on my machine at least, right? So that's how it goes. All right, so we can use the same size. But I think I also have to include some stuff for the page size. Yeah, I need to include the uni-std. Right, and it's a platform dependent thing, so I'm going to put it in here. Man, uni-std. All right, so is it going to compile now? What else do we have in here? Context. Okay, so this has to be a G, right? So I just copy pasted mindlessly some code. All right, so just like LLM chat. Mom, look, I'm LLM. Oh. So what this thing, yeah, so this function does not accept generator anymore, and look at that, it compiles. It fucking compiles. So if I try to run it, I think it's going to crash because it will create the generator, but then it will try to call generator next, which is not implemented, right? So if I just try to run it, generator, there we go, and it fails in here. But I'm kind of curious, like, what exactly does it create? So what's inside of this object? We might as well just, you know, do gf2 generator, a boom. Let's break it main and let's run this shit. Okay, so let's see what we have in here. I wish I could just configure something to actually make this specific window of this size and this position somehow in GF, but I don't know. Right, so all of that is null, and this is what we've got in here, right? So this is RSP, and this is our, you know, stack base, and there's a little bit of information in there. Okay, so everything seems to be initialized correctly. Dead is false, so this entire thing is not dead, which is nice. All right, this one is interesting. Since we're doing generator next, we definitely need to now push that generator. We need to push that generator to to the stack, right? So we have to do something like di append generator stack G, right? And then we have to switch the context of the execution to that thing. But furthermore, we need to somehow be able to then return back to this thing. Right, so the question is, how the fuck are we going to be doing all that? How the fuck are we going to be doing all that? We need to save the current execution environment of the main thing in here. And I feel like the current thing in here should be one of the generators. Right, it has to be on the stack, doesn't it? It has to be on the stack. But I'm not sure how exactly I'm gonna go about that. And by the way, I'm already streaming for 1 hour, which means that I want to make a small break and refill my cup of tea and stuff like that. So I'm gonna think while I'm making a cup of tea how to organize all of that. But I think I'm getting an idea. So this generator stack is probably going to contain a generator for this. Yeah, so the main executing thread is also a generator that has to be on that generator stack. And generator creation create while loop that every 100 milliseconds switch the context. We can do something like that, right? So you can kind of end up with pretty interesting concept in here using generators, which can replace the coroutines that we had in here. Generator init, yeah, we need some sort of a generator init, which will put. Yeah, you're right. We need a generator init which will push the thing in there. God damn it! I was hoping that we'll not need a generator init, but apparently we do need generator init. Right. So let's actually do this thing. So void generator init. Right. So this thing should not return anything, and for now it is not implemented. Generator init. Right. So and what you do in here, we just do generator init. It just pushes the currently executing thing, right, to the stack. So and in the coroutines, when I do coroutine init, right. Oh, and this is actually kind of funny. Well, yeah, we probably don't even have to do anything in here. Right, so we just need to push a new generator, because then when I do generator next, what I have to do, I have to save the current execution environment to this generator thingy in here. Right, and then just, yeah, I think we can do that. All right, so yeah, I need to think a little bit, and after the break, we're gonna continue doing all of that stuff. Okay. All right, let's fucking go. What we need to do, I think when I do the generator init, what I just have to do, I just have to push an empty generator into this entire thing. So I suppose just like a 0 generator should be enough. Right. It's kind of funny how I wanted to get rid of the global array of the context, and I still ended up with the global array of context, but for a different reason. Looks like I can't really escape the global array of contexts. Anyway, so the append, so I'm gonna take the point to this entire thing, and let's actually maybe create a generator. Yeah, so this is a collateral, and this is just like that. There we go. So we just append that, and it's gonna be empty. I'm not gonna try to capture any of the environment in here, because I'm pretty sure I'll have to capture it anyway when I do yield or next or anything like that. So I don't have to do anything in here. So we just do init, and that just allocates a new thing in here. Yeah, actually they are pointers, pointers. They are pointers. So which means that maybe what I have to do is just malloc this thing. Yeah, let's go. Right, so I'm just gonna malloc it, then mem set it to 0, and then I'm going to push G in here. That's what I have to do, right? So because it's a stack of the pointers to the generator. Yeah. Okay, so generator next. Okay, that's understandable. So when you call generator next, what we have to do, we have to capture the current environment, kind of in a similar fashion as we do with yield. Yeah, so it has to be a naked function with an assembly body. That sounds funny, but that's true. That's exactly what it has to be. It has to be a naked function with a beautiful assembly body. This sounds so fucking funny. Anyway, so let's go ahead and just do that. Sounds kinky. Damn. Okay, so this is gonna be generator next. Okay, so and this one is a generator G, generator G, which is rather interesting, isn't it? So we probably have to, so since it's a next, right, since it's a next, we just pass the parameter. This is the first parameter, so it's going to be in RDI. So it is going to be in RDI. But we're kind of saving the current RSP in RDI. So how capturing the environment works? What we do, we enter the function, and since it's naked, it doesn't have any sort of like, what is the prologue and epilogue, right? It doesn't have any prologue and epilogue, so that means it just starts with this instruction right away. That's kind of the point, right? So yeah, that's what it is. So I'm from Ukraine. Welcome. I hope you're safe. So we push in all of these things, but in RDI, we have this pointed to the generator. We have this pointed to the generator. So what we have to do, we probably have to move the RDI into RSI. That's what we have to do. So let's actually see. Move Q. RDI into RSI, because I think RSI is the second argument in here, right? It is the second argument. And then we're moving RSP into RDI. And then we have to be switching into a thing that actually performs the generator next, I think. I think that's what we have to do. I think that's what we have to do, but I'm not really sure how we're going to be calling this entire thing. So generator switch context. Maybe we can call it generator switch context, because why not? So by the way, I need to have a call convention like in front of me so I don't forget this entire stuff. All right, so I take RDI. This is going to be the second argument. That's kind of important. To be fair, maybe not. Right, so what if I make RSP the second argument? So that means it has to be RSI, so I don't have to have this extra instruction. Saving up on extra instructions, saving up on nanoseconds, right? Anyways, so let's grab this name. Let's grab this name and put it in here. So that means the generator becomes the second argument in here, right? And then we have RSP in here. So that's pretty cool. And I think it kind of works out very naturally. So I'm going to do generator switch context, right? Because what we have to do now, we have to take the top of the generator stack and save this RSP on the top of the generator stack and switch, restore the context of this new generator. That is actually very fucking naturally, isn't it? I think it is. It's so cool, actually. But anyway, let's try to actually compile this entire thing and run it. So G, it complains about unused stuff a little bit, but that's fine, right? So it's just like, it doesn't see what's going on in this assembly. right? Because it's just a text for the compiler, unfortunately. So it's not really powerful. Though a built-in assembly in something like Jai actually probably powerful enough that it can detect that a variable is used within that assembly. Right, so we can even take a look at the, like how assembly works in Jai. Like Jai built-in assembly is fucking bananas, I'm telling you. So assembly, yeah, inline assembly. So yeah, let's actually see. So here's the first instruction, a 64-bit immediate to general purpose register move. The apple is our named general purpose register. We do automatic register mapping so you can use familiar high-level names just like you do in regular programming. Just think for a moment, what the fuck is the implication in here? You moving 10 into some sort of a general purpose register, but you don't know which one. You asking compiler, please compiler, allocate me a whatever register that is free right now, according to how you generate this function. And then as you refer to this name, it's going to be the same allocated register for you. So, like, in what fucking language, within a built-in assembly, you can communicate with a fucking register allocator of a compiler? Just think about that. This is insane. Like, I've never seen that anywhere. GCC has something similar. Oh, okay. So, I mean, that I just... okay, so I'm just stupid then. That's fine. I kind of got used to that. So, anyway... But it's kind of cool. Just saying. You can also use variables in here and stuff like that. Then you can subtract apple from banana and add count to banana and stuff like that. So, yeah, it's pretty cool. It's a pretty cool assembly. What if you want racks directly? I think you can just like you know, refer to racks directly if you want to. Yeah. So there's also implicit 0 traditionally set through. Do we? They don't demonstrate that how to refer to racks directly, but I'm pretty sure they refer to racks directly somewhere in the module. So we can do racks. Excuse me. So this is how we do that, I suppose. It's pretty dense, honestly. It's pretty noisy. So I suppose it's like the size of the move and stuff like that. It's equals. There's a lot of things. Oh my god, Cisco! What the fuck? There is a Cisco instruction and you provide like registers as arguments. Man, I need to do a stream on Jai assembly because this is fascinating. There's a lot of things to unpack in here. It's kind of cool, honestly. But anyway. So let's continue the development. So yeah, let's go ahead and just like try to run whatever we got. So it's not even runnable, right? So this one is unused. But I mean, it did in fact try to run. So this is RSP. So are you fine? What's up with that? So conflicting names. Oh yeah, so now we have these two things. Yeah, so these things should not exist anymore, I believe. Right, so first, when you do next, we capturing the current environment, right? So just capturing the current environment. So it doesn't like something about long, and this is because this thing is supposed to return void, actually, void star. Can I do something like that? Yeah, I can. There we go. So, and as we ran this entire thing, we actually stopped at switch context. So that means that we managed to call generator next, and now we have this switch context. In fact, maybe I want to take a look at what do we have in here. So I'm going to just do that, and I'm going to break at main, and also going to break at switch context, right, at these two things. I'm going to run this entire stuff, and there we go. So we do the generator init. We can take a look at the generator stack. Generator stack, is that what it is? Yeah, there we go. So as I initialize the whole thing, so we got the first thing in here, which is a generator, but I can't really, you know, unwrap it for whatever reason, because it's a single thing in here, but whatever. So then I do generator create, and this is G. So we can take a look at some of the parameters in here, specifically stack base, right? So I think stack base is kind of important. I'm gonna just like literally do stack base, and I'm going to print it, and I'm gonna print it for the sole purpose of copy pasting its address in here. Right, so then I can confirm that that's the same thing in here. Okay, so then I'm gonna continue execution, and obviously I stop at generator switch context, and what I do in here, I essentially have pointer to G and RSP. So, and the question is, if I do p stack base, is that the same address that I actually saved before? It is. So that means it passed all of the information to this function correctly. So everything is fine here. So when we confirm that in a debugger. Okay, it's nice to have some sort of a debugger, right? So GF is not near to something like a RAD debugger, right? So because RAD debugger is not really supported on Linux yet, but at least it is something. Why GRSP is different from RSP? Because it's two different RSPs. Because we have separate stacks for each individual generator. We have separate stack. Red debugger. You don't know what about red debugger? Red debugger, debugger, epic, something. So this one. So native user mode multiprocess graphical debugger by Epic Games. Actually, right, so they developing this thing, and it's bananas, I'm fucking telling you. I wonder if there's some demos. So they don't really advertise any demos in here, but there's like a lot of videos online about this debugger, and it's fucking cool, right? It has its own like a UI and everything. So, and they do not support Linux, it's purely Windows, right? So because it's a, you know, Epic Studios, right? They're making game and stuff like that for Windows, but they do plan to have Linux support at some point, right? So Linux debugger. So I'm gonna put that in the description for people on YouTube, obviously, right? Anyways. So what do we need to do in here? So RSP is RSP of the currently saved environment. We haven't switched to the next generator yet. So what we have to do, we have to take the generator stack, right? So we generate a stack, and we have to take the top of the stack. We have to take the top of the stack, and top of the stack contains the thing that is currently executing. Right, so, and I'm gonna take this kind of thing. So this is the count, and I'm gonna take its RSP, and it's probably a pointer, and I'm gonna save this RSP in here, right? I'm saving this RSP in here. And here's the cool thing. So what I need to do now, I need to do di append onto the generator stack, right? So this is the stack of the generators, and we're just appending this G in here, right? And after that, I have to like basically restore the context of that generator. That's what I have to do. So generator restore context. We don't have that function yet, but we're gonna have it soon. Context G RSP. Yes. And this thing is not going to return because it's also going to be like a naked function. So it's going to be based on the coroutine restore context. Restore context, this one. So it's going to be based on this one. And I think it's going to be literally just that. Right. So, but it's going to be just like a generator. Restore context and just RSP. Okay, that's very cool. That is very cool, actually. Okay, guys, so now, and it's pretty cool. That's very cool. I wonder where exactly it's segfaulted. We can put something like to do in here, right? So something like test, like a Kawabunga development. So it didn't fail here. Did it fail here? No. Did it fail somewhere here? Yes, it actually failed somewhere here. Surprisingly. And I know why. Because I forgot to do -1. Honestly, like taking the last element on the dynamic array is kind of an annoying thing. I was thinking that I maybe need to introduce some sort of like a macro, di, maybe like a last. So it's going to accept da, right? So what it's going to do is just like basically items, right? And it's going to take the whole thing in here, count -1. Right, and that's a good idea, I think. I think that's a good idea. Yeah, and we need to make it part of the knob, but I'm not really sure how often do I need to do that. Like, I feel like I need to do that often, but I don't know. I don't have a concrete data. So that way I can do stuff like this. Right, so just take the last thing. Alright, and I don't have to worry. Yeah, so that kind of works. And I assume it to be a pointer because like the I append assumes it to be a pointer. So I think it's fair to assume that it is a pointer. So let me double check that the last actually does -1. Okay, so now if I do something like this, okay, that's totally fine. That is totally fine. And I think now if I try to restore the context, it's generated yield. I actually fixed segfault without a debugger. That was easy. So, well, I mean, I was just lucky. I was just lucky that I instantly noticed that. Didn't spend 3 hours debugging, but it was not a semicolon anyway, so that's fine. Kek fault, exactly. Kek fault. So, yeah, so you know what that means, right? It failed at yield. And where do we call yield? Where do we call yield? We call it within the generator, chat. So that means it actually went into the generator, into the actual function of the generator. So that means we can just like call that this thing, like break at fib, run this entire thing, and we're inside of the generator. So yeah, that's pretty cool. We can go here and then into the yield, and yield is not implemented. Boom. So we just need to implement the yield. All right, let's go ahead and do that. So yield also need to capture the current environment. Kinda. It also need to capture the current environment, but on top of that, it also accepts the argument. It also accepts the argument. So yeah, let me see. I'm going to grab this thing, and I'm gonna do the copy paste. So this is the generator yield now, but it accepts the void arg. It accepts the void arg. All right, so what are we doing here? So it has arg unused, and that's totally fine. We save the environment. We move RSP into RSI, which is the second argument. Yes, it is the second argument, and the first argument is here. And here we do switch context, but this is not what we have to do. So we have to move to somewhere else. Maybe return, yeah, generator return, because this is what you want to do, like a yield return. So, and it is going to, well, this thing doesn't really return anything here. That's kind of important. So generator return, it accepts void arg that we, basically forwarded from the yield, and then it accepts the RSP, right? So the RSP of the whole thing. So, and what a return has to do, it has to take whatever we have on the top of the stack, right? Di last, right? So it does di last, and yeah, di last. So of the generator stack. So this is the last thing, and we set its RSP to this. Okay, we set its RSP to this. After that, we have to pop an element out of the generator stack. So we have to do count -1. After that, we have to take the last thing again, and this is the thing that we have to kind of restore. Right, generator restore context. Generator restore context, but not really. Not really, because now we also need to return arg. We need to return arg. So it's going to be restore with return. That's kind of important. It has to be restore, but with return. So we need to make a copy of that thing. So restore context. So restore, and how should we call it? Restore context, let's call it with return, right? So with return. And right, so this is going to be void star, and this is the argument that we're trying to return. So restore, but with return. Okay, so that's pretty cool. So return with return. So this is RSP, and then we do arg in here. Okay, that's fair. So we take RDI, we move it into RSP, and we have to take RSI, which is the second argument, and move it to rags, because rags is the register through which we return the value on x86-64. And I think that's it, right? So the naming is a little bit ass in here. The naming is a little bit ass, but I think that's roughly what we need to do in here. So by the way, this stuff, I suppose we can say that this is unused, and this is arg. All right, so let's just try to build it, and it builds actually. It actually builds. One of the things I want to do, I want to maybe step through everything. I would love to just step through everything and confirm that it works exactly as I expect it to work, and luckily wouldn't have to step through too much stuff. All right, so let me rebuild everything, and I'm going to do generator, and I'm going to break at main. Right, so let's go. Okay, so we have that, generator next. I'm stepping into the generator next. Cool. So I might actually take, yeah, so here is the assembly. I can actually switch between, yeah, so it's kind of funny. So this is the text. I enable assembly mode, and I can see exactly the assembly that I have in here. So that's cool. Oh, fuck. All right, so I kind of pressed N, so which means I skipped this entire instruction, and I didn't step by the by the individual instructions. I fucked up in here, but it didn't segfault so far, so everything's fine. Okay, so we're inside of the switch context. We're gonna switch into the what is it called, generator soon. So I'm gonna step into this thing. Okay, so I'm basically restoring the environment, and at some point I'm gonna jump into the generator. Okay, I'm inside of the generator. Cool. I'm actually preparing to generate the first value out of the Fibonacci sequence. I'm stepping into the generator yield. All right, so generator yield, what it does, it saves the environment, right? It saves the environment, and it steps into the generator return. Okay, so we do a generator return. So we save that environment, we pop a value, and we're about to do restore with the return, right? So I'm stepping into that. So this is the thing that we have. And I would like to maybe inspect the value of arg, and it's 0 actually. RSP is some sort of a stack, which is perfect. And I expected the argument to be 0 because the first value that we print in here is in fact 0. Right, so let's actually step through all of these things, and hopefully it is going to actually at some point return and print the value 0. And did it do that? I didn't see the value 0, but maybe the debugger didn't really print it, but we didn't segfold anyway, which is already kind of a win in my opinion. So, all right. So I stepped through the debugger. We didn't touch any memory in any weird places, so the operating system didn't slap us in the face. Right, so there was no segfault, which is already kind of cool. So that means if I try to just run the generator, it is going to just return 0. And it did in fact return 0. So we kind of polled the generator. So what if we poll the generator several times? It should print several Fibonacci. Okay, look at that. So it's starting to print Fibonacci. So it is printing Fibonacci. So that's kind of cool. So it is like in Python, right? So you have a function, you turn that function into generator, and it's just like that generator just stores the state of the executing of the function. You can then poll that generator. You can tell the generator, okay, go execute something up until the next yield, and the next yield will return from that next, giving you the next value. So we literally implemented Python-style generators in C, and it kind of worked. So it's not going to work up until the moment we need to return, right? So yeah, so here we have generate a finish. We have generate a finish, and it's not implemented yet. So let's actually try to do the following thing. I'm gonna just keep polling it like until forever. Ideally, honestly, ideally, I want to be able to do the following thing. While G is not dead, keep polling it. And I'm hoping that the finish function, as it returns, is going to essentially take the current generator and mark it as dead. So then whoever is calling that function, knows that it's time to stop doing this entire thing. I think it's kind of cool interface. Right, so you have a generator and you check in, is it dead? Is it dead? Or it's not dead? Well, we keep polling. All right, so let's give it a try. That's pretty cool. Right, so it was generating Fibonacci up until the next Fibonacci number became bigger or equal to 1 million. And then it returned into the generator finish. And this is where we have to finalize the generator. So it's actually rather easy because the current generator is the top at the generator stack, right? Generator stack. We can just literally mark it as dead now, right? It is dead. So then we can pop that generator out of the stack, and simply just, yeah, return from that stack. But what do we even return from that stack then? So that's kind of interesting. So is it going to... So that means that value is kind of bogus value. That's what's funny about it. Oh yeah, that also would be actually kind of cool. Yeah, it would be kind of cool to implement some sort of a macro that hides that polling of the generator. So that is fucking poggers, honestly. And ironically, that's a cool idea. Thank you. So, and here is the problem in here is that you only may know that it's dead when you try to poll it for the next time. That's kind of the problem. So that means you kind of poll it. Right, so you have to do like true in here. So you try to poll it and you get a value, some sort of a value. Right. And you have to check, is it dead after that? If it's dead after that, you break out of the loop. And if it's not dead, then that value is not bogus. It's amogus. Right. So that's kind of what it implies, right? Because you can't know if it's finished or not until you do that last poll. And that last poll will tell you through the dead that, yeah, so that's what it is. Yeah. Well, I mean, if we're going to kind of hide that behind the macro, maybe it doesn't matter. You know what I mean? If we're going to hide it behind the macro, maybe it doesn't matter, but we'll see. Do while, I don't know. I don't know how that macro is going to look like though, so... No, I don't think you're stupid. It's just like it's kind of difficult to predict how exactly the macro is going to look like. Oh, you mean do while in here? Nah, not really. Because you need to at least try it, but not fully finish it. You can't implement it with do while, right? So how is it going to look with do while? You try that, and then you need to check whether you have to exit. No, you can't do that with do while. It's kind of, yeah, it's kind of difficult. But I see what you're trying to say. Okay, so it's done. So the only problem here is that now the generator is not really finalized. So what you have to do is maybe have something like a generator destroy, right? Which accepts the generator and just cleans up the memory after that and stuff like this. Right, we can implement that. So generator create. It's not Python, right? So we don't have a garbage collector in here. So we have to clean everything ourselves. And in here, we only need to unmap the stack, which is kind of, kind of difficult, right? So because if it grew past its stack base, so we're gonna leak a bunch of pages. Because of that, I'm starting to think that maybe grows down is not a particularly great idea, right? So yeah. it's not a particularly great idea because like it's better to just allocate a bunch of pages and mark the first page as protected and just like use that as a guard page. So I think at some point I will have to get rid of the grows down, right? Because it's how difficult it is to just then deallocate because it can leak a bunch of pages. Anyways, so we have to unmap the whole thing. Mon map. All right. So mon map, the address is stack base, the length is a generator stack capacity. Right, so we're gonna do that, and then we're gonna free G. So yeah, that's it. So I don't think we allocated anything anywhere. So we only allocated the stack and the generator itself. Which also probably means that maybe we have to pass the generator as the structure, but I mean, that means I have to work with the structure from assembly, which is annoying, and on different platforms it's different. All right, so that's pretty poggers. Okay, let's try to run it one more time. One more time. Okay, that's cool. How can we wrap all of that scheiße into a macro? How can we wrap it into a macro? Can we do just like a for in here? Right, so we can say, all right, this is the first thing. Aha, and this one is kind of cool. While, ooh. Bro, what the fuck? Wait a second. We were thinking about do while. Oh, okay, people also suggesting for, okay, so it's, damn, I'm actually impressed how naturally it just, okay, so, so we can do define for each G, and we can just simply, you know, put that behind this thing. So, and obviously we probably need to have some sort of like an iterator, right? So it's called it. So this becomes it, G, and I probably would like to wrap it just in case. So then I can do for each it G, and this is just it. Well, I mean, I originally called it a value, so that means it has to be a value like that. Bro, this is OP. What the fuck? Okay, let me actually bring this thing a little bit closer so you can see exactly what the fuck am I doing here. Look at that. I have a function that generates Fibonacci sequence. Just think about it for a moment. I have a function that generates Fibonacci sequence and it yields them. Then I create a generator out of that function, an object. And then I can for each that object, and all of that is entirely in C. Missed the second it. Oh fuck, but it worked somehow. I wonder how the fuck it worked then. How the fuck it worked, excuse me? Ah, because I called it it worked accidentally. The best kind of worked. It worked accidentally. Damn, this is so fucking... Who needs Python? Right. Who needs Python? This is so cool. It's kind of like coroutines, but it's different. It's coroutines from a different angle. Have you noticed that? Like, and this is the reason why I didn't want to actually put it into the original coroutines library, because it's kind of a similar thing, but it's from a different angle. Right, the idea, the underlying idea is the same of capturing the environment, saving it somewhere, and then restoring it. But the API is different. It's like an approach is different. Question of the decade, who needs Python? It's a good question. It's like, the case of Python is rather bizarre. It is rather bizarre. It's like you don't really need Python, and Python is a horrible language, honestly. Syntactically, semantically, it's an absolute trash language. But for whatever fucking reason, probably for a meme, people implemented shed ton of bindings for different libraries and wrote shed ton of code to the point that it's just like, it's pretty convenient to use Python because of all of the code that is written in Python. It's kind of interesting. I feel like I keep comparing languages to cryptocurrencies. And they are like cryptocurrencies on a much deeper level than I originally envisioned. It's not only about the hype around languages, but also, so the more code you write in that language, the more you kind of being dependent on the infrastructure of the language. It's kind of similar to the blockchain, right? So the infrastructure around the language, building infrastructure around the language is like building a blockchain for a specific cryptocurrency. Proof of code. Right. And what's funny is that it's like over time it becomes more and more difficult to like stack upon that infrastructure and work with that infrastructure and stuff like that. So yeah, it's kind of interesting. It's literally just the most used language by non-programmers, yeah. Python is so immortal, even Python 2 won that. Exactly. It's a phenomenon. It's a phenomenon of its own. So I got some subs. Let me actually quickly acknowledge the subs. People been subscribing. Not that many though. Stupid Engineer, thank you so much for trying with the message. Yo, just passed algorithm and data structure exam in C. Congrats, my friend. In part thanks to you. Really, thank you. Right, thank you so much. Well, what's funny is that I hear a lot of people from around the world, like students, university students, thanking me for my videos and for my explanations and stuff like that. What's funny is that I graduated from a pretty shitty university. So our algorithms and data structure course consisted pretty much of sorting algorithms in Delphi 7, and that's basically it. That's how crappy it was, and it was embarrassing. So we didn't learn basically anything. It's just like it's a shitty local university that is funded by the government, and it's like literally free, and it's just like people who graduate from there, they can't really like work easily in the industry unless they actually were self-taught. And it's kind of bizarre that me, being literal nobody, graduated from a shitty university, and people all around the world thanking me for what I do. It's kind of fun. I don't know what to make up of that. It's kind of the irony. The God has a great sense of humor. Thank you, God. That's very funny. But anyway. Or maybe universe, right? It depends on how religious or not religious you are. I don't think there's that much difference between saying universe or God. It's just like pretty much the same thing. Anyways. So what else can we do in here? What else can we do? So, and we implemented stack actually for a reason, honestly. We implemented stack for a reason. So then we can actually kind of have like a nested generators. And how can we implement the nested generators? That's a good question. We can... Okay, so I'm about to yield A, but then I don't even know what to do with that, right? So is there any good, interesting examples of the nested generators? Recursive Fibonacci. This is not going to test the stack of the generators though. It is going to test the stack of one single generator, right? But it's not going to test the stack of the generators. We can implement like the Fibonacci thingy. It's not that hard. So I'm gonna maybe create a fib void arg, and it just like tells you like the Fibonacci that you need to implement. So what we need to do, we need to do long n, and this is basically arg, and it's long. long dong. What's funny is that it's a valid C, right? Long dong. Right, if n is, let's do it like this, less or equal than 0, I guess it just like returns that. If n is equal to 1, it returns, let's just returns itself. Maybe we can say, okay, if it's less or equal than 1, it returns itself. I haven't implemented recursive Fibonacci for a while, so let me just reinvent it myself, okay? Okay, just cut me some slack. Then, oh, this one is funny. How do I even return it then? So that means I have to do generator yield. Oh, Fibonacci. Is that how you do that? N minus 1 void, and you can't really do the recursive one with yields and shit. Yeah, you can't really do that, I think. Yeah, you can't do that. So because you need to. Python lets yield return a value, but it's not really returning it, returning it out of the next. I don't think it works like that. I don't think it works like that. I think we have to do it like this. Anyway, so what I want you to do in here is that on each sort of like yield, I want you to maybe create another generator for something else, right? What could that be a generator? What kind of generator could that be? We could do just like print that value like n times. That's one of the things we can do. Repeat, let's call it repeat with arg. So, and what do we do in here? We can repeat it like repeat 3 times, sort of repeat 3 times. We're gonna do size t, and it doesn't even matter what exactly we repeat in here. We'll just do generator yield arg. That's a very abstract way of writing that, by the way. So this generator specifically doesn't even care what exactly you pass into it. It just repeats that thing 3 times. What's funny is that you can just say repeat and do while true. Maybe you can even call it forever. Look at that. Look at that, motherfucker. And this is a very powerful generator, because you can poll it as many times as you want. So it's kind of like a, yeah. And then at some point when you're kind of done working with that generator, you can throw it away, right? So it's never gonna like go indefinitely. It's gonna go for as long as you let it go, as you poll it. It's basically iterators, but I mean, we are writing imperative C code. So that's what's cool about it. It's like it looks like an actual like C code. Okay, that's kind of cool. So let's create an internal generator in here. Let's create an internal generator, and it's going to be like a forever. And what I'm going to pass in there, actually, I'm going to pass this thing, right? So it's going to be G, and then I'm going to do generator next. So the reason why I want to do that is because, so long results of some sort, so it's going to be 0, and I'm going to just do result plus, and I'm going to just do that 3 times. Then I'm going to generate a destroy G. So the reason why I'm doing all of that is to test how do you use generators within the generator, so then we can see that stack of the generators actually work. It's kind of meaningless, right? So, but here we have a generator, then we call another generator within the generator. So, and yeah. and the stack unwinds and stuff like that. So yeah, you can have like a top take and drop generators and stuff like that. You can kind of organize like a Haskell style thing. That's kind of cool. Wait a second. Okay, so this is the forever generator, and so if you do take, how can you combine them together? So take has to be something like a generator, right? So it's a generator G, and it takes the amount of like how many times you want to pull that specific generator. But that means it also has to collect the values out of it. So yes. But anyways, so I just want to test this kind of thing. So it's a result, and we actually yielding the result out of this entire stuff. Right. So instead of yielding A, we are passing A into a forever generator that just repeats that forever. We repeat it 3 times, accumulating it 3 times, multiplying it by 3. Then we destroy that generator, and then we yielding the result of that sum from the Fibonacci generator. Does it make sense? I think it kind of makes sense. So, see, so this is one generator, right? So within the generator, we use another generator, and so on and so forth. So W points for free memory before quitting. I guess, well, I mean, we don't have to free any memory. So, so let me try to rebuild the whole thing. Right. Okay, so that seems to be building. So now if I try to run it, so we had 0, 1, 1, now it's actually multiplied by 3. So it works. So if we get rid of this generator, this entire thing, and just like use A as the result, right? So we're not creating any inner generator. It's a 0, 1, 1, 2, 3. Then if we make that a generator, now they are multiplied by 3. Polling a generator within a generator works, so the entire stack scheme, right, so the stack actually works. And maybe potentially this entire thing is going to work in multi-threaded environment because we have a thread local. And if I remember correctly how thread local works, it basically creates a copy of this variable for each individual thread. So if I understand correctly, so is this how thread local works? Let me double check. So convenience macro, okay, so thread local storage duration. So let's actually read about that. Storage class specify storage class. I mean, it's describing it from the point of view C++. Ew, yikes. A previous declaration and compound literals expression since C23. At most, one specifier must be used. Okay, so this is boring. What does it mean? Storage duration. Every object has a property called storage duration, which limits the object lifetime. There are 4 kinds of storage: automatic, static, thread. Okay. Thread storage duration. The storage duration is the entire execution of the thread in which it was created, and the value stored in the object is initialized when the thread is started. Each thread has its own distinct object. So if we are in multi-threaded environment, each individual thread is going to have its own copy of generator stack, which means this entire thing will work in multi-threaded environment. Well, if they're not trying to like interact with each other between different threads and shit like that. So thread local creates its own sections in BSS and init section. Okay, that's actually pretty cool. Okay. Damn, this is... So can you now use this kind of generators for like networking? Can you have a socket that is generator? That is really interesting. So I have an echo server, right, implemented using coroutines. Yeah, so is it possible to make it async IO compatible? That's the question I'm trying to ask. Thank you so much. That's the question I'm trying to ask. Can you make it async IO compatible? So the scheduler, so that means you need to create like an additional entity that is the scheduler that is managing all of these generators. But it's kind of cool. So the generator could be now a socket that just yields you know, the messages that it read from, but then how do you write into that socket? So that's also an interesting thing. Generator yield should be able to return a value that you pass into the generator next. Oh, that you pass to the generator next, but this is exactly what we do. We pass the generator, but in Python, here's the interesting question. Here's an interesting question in Python. If I take that, Python 3. Okay, so for the first n, and I've got the generator. All right, so if I take a look at the methods in here, so it has next. I know that it has next. Right, so next. So it's a method. If I take a look at its help, it doesn't accept any parameters per se. So in Python, you have send. Oh shit! What the fuck? How do I accept it? How do I receive it? So okay, so when I do send, it's a result of oh wait the fuck, really? What the fuck? That is cool. So that potentially can make yield and next kind of the same thing. We can even reuse some of this code. Okay, so that's kind of cool. There's some stuff to think about in here. But this is a different approach. It's a coroutines approach, but it's a different approach. I'm really glad that I decided to explore today. Right, like when I started today's stream, I wasn't sure if I will have enough content for 2 hours, but apparently this is actually a very interesting and deep topic, right? So yeah, that's kind of interesting. I'll need to think about it. I'll need to process what I discovered on today's stream, but it's a really cool concept. So it's a different alternative approach to coroutines. Not sure if I'm going to be using it. Not sure if I'm going to be using it, but it's still interesting to explore nonetheless. In my opinion, it's still interesting to explore nonetheless. So, but I think I'm going to call it a day, right? So because I'm already streaming for more than 2 hours, right? So I don't want to, you know, over stress myself. So we haven't rated anybody for quite some time. So do any recreational programmers streaming right now? Do we have any recreational programmers streaming right now? So I don't know who's streaming. So Valigo streaming. I think Last Miles streaming. Last Miles doing chess. Valigo streaming, he's doing Jai. So, and I do approve of that. So let's actually rate Valigo. I'm gonna. Where's my Twitch.tv? So what is he doing right now? So we'll actually see. We'll actually see. So how do you rate? Raid Valigo. All right, so get ready for the raid, boys and girls. Get ready for the raid, and I see you all on the next recreation programming session with Ahu Mr. Azozin. I love you all. Mwah. All right, this is the footnote of the session, and I would like to try to implement something that the chat suggested to implement, which is the ability to send values into the generator. Right, so as an example, let's just quickly implement something like, I don't know, square generator, which essentially what it does, right, it accepts the value that you send into it and doubles it. Right, so maybe the initial value could be sent through the argument, right? So we can do something like this. We're gonna cast the initial argument to that, and we're going to generate yield, and basically send the square value of this thing. Right, and essentially the suggestion is let the generator yield return a value that you send through the generator next. Right, so the extend generator next with the value in here, right, and let the yield return that. So that means next, the yield is going to return the next value that the polar of the generator sent it, and then we can repeat the entire process. Essentially, we repeat the entire process. So, and those we get the sort of the generator that gets the values and then squares them and sends them back. Right. So we need to implement something like this. So the way you would use something like this is by similarly creating a generator out of square and maybe start with a 0. Well, let's start with 0, then we're going to iterate from 1 to, let's say, 10, including 10, and then we're going to be doing generator next. So this is a G, and we have to send the next value. So let me actually make it long in here. I'm going to take this thing and cast it to I. And through this thing, we're going to get the double X, right? So this is the double X. Maybe I'm going to call it X for the consistency. So this is the X that we're sending, and we're getting the square of the X. Right, and then I'm going to just like print this entire thing in here, LD. So implementing all of that stuff is not that difficult. We already know how to restore the context with the return. We literally have this kind of thing with return. So it's not that big of a deal. Just like employ that in the generator yield, right? Because as of right now, generator yield, I think it just uses restore context. Or maybe it's next. I think it's the next who's using just restore context, right? So here's the next. Then it says switch the context, and within the switch the context, it does return restore the context. So just employ return context with returning here. But there's a little bit of a problem. Right, there's two situations when we restore the execution of the generator. The first situation is when we just created the generator, and restoring the execution is going to start from here, from the beginning of the function. And the second situation is when you restoring from the yield. Here is the thing. We need to return a value when we're restoring from the yield. But when we're restoring for the first time, just to start the execution of the generator, we have no place to return anything because here we don't have any function call. And the way we return values from a function call is by storing that value into rax. When you start executing of the function, the start of the function, the prologue doesn't look at rax. Rax is reserved specifically for returning the value. So generator next has to kind of distinguish between being restored for the first time and being restored from the yield somehow. One of the things we can do, we can maybe separate these two operations. Generator next is going to do a return without any value, and generator send is going to do return with the value. So this is one of the things we can do. Or another thing is that we can probably employ something interesting. So for the generator, we could introduce something like fresh, sort of speak, something like fresh. And when I create a new generator, I actually mark that generator as fresh. So this one is true. So, and through this flag, when I do generator next, right, so I do generator next, I capture the environment, capture this entire environment and do to the generator switch context, right. I can now distinguish between these two things. If it is a fresh thing, I'm doing this kind of stuff. If it is not fresh, I probably have to return from somewhere. I have to supply a value in here. Right, so when I don't have that value anywhere, right, I'll probably have to accept that value from here somehow. We'll see how we can do that. So this is restore the context with the return. Restore the context with return, it accepts the argument in here, it accepts RSP and stuff like that. And since right, we already did the fresh, what I have to do in here is just I have to do fresh false. So the next time you try to switch the context is not going to do that. Okay, so we don't really have an argument in here. So how are we going to approach this entire stuff? So here's the generator next. Right, so the first argument is located in RDI. The second argument is going to be located in RSI. So what we do in here, we take the stack pointer and put it into the RSI, effectively overwriting arg. And we do that because we didn't have arg before. So now we do have arg before. So what I'm thinking is that we need to pass the RSP via the third argument of the call convention. So we're going to move it into RDX. Right, so now we have G, arg, and RSP, and then we're calling into the switch context. Yeah, okay, so that means I have to actually kind of switch the order of these things, right? So because these are arguments exactly as in the next, right? So they go into the same order, RDI, RSI, and then into the RDX we put RSP, and that's why we have RSP in here. Okay, makes sense to me. So we're storing the current execution environment and stuff like that. So, and if we're doing that for the first time with the fresh thing, we don't really do anything with that argument, which effectively means we kind of lose the first argument you actually pass in there. Right. So, and the first argument you have to take is the one that you accept through here. So that's going to be your first argument, which is kind of interesting, which makes me think, what if when you create the thing for the first time, you don't pass this argument in here? Bro, this is kind of cool. What if that argument that you pass to the generator is not passed through create, but through the first generator next? And it's passed as, okay, this is actually kind of cool. Damn, this is cool. Wait a second. So, and essentially here, what I can do is I can just do something like this. Right. So I just create, nothing is passed there yet. I do the first generator next, and if the first generator next is going to pass the value into the arg, the next generator next is going to pass it through the return of the yield. Can your Python do, how does Python even distinguish this kind of stuff? So I don't really know, I don't know Python, but this is kind of cool. Right, okay, so let me see how we can approach that. So generator next, right, here's the argument, we pass the argument. So switch the context, And what we have to do in here, now we have to take the arg and put it onto the stack. But where do we store that thing on the stack? All right, so generator create. So yeah, it's RDI in here. Look at that. It is RDI in here. So yeah, this is going to be effectively like 0 since we don't have arg. What we have to do in the next, when you're doing fresh, we have to take its RSP and find this specific slot, the RDI of the slot, and write something in there. So I wonder how we can pull that off. Let me actually see. Generator switch context. Here it is. So this is fresh. What I have to have in here, I have to take this RSP yet again like this. So this is my RSP. But it's not that useful. I think what I have to do in here, I have to repeat this sort of trick that we did in create. Okay, so now RSP is pointing at the very far right. So this is basically the stack, right? So this is the stack base, right? So this is the stack base, and RSP is now in here. So this is RSP. So what I have to do, I have to subtract this thing once. Let me remove this kind of thing in here. Right, subtract it once to get to this return address, then subtract twice to get to this one, and subtract thrice, right, to get to RDI. So I have to do RSP -3. It's very much hard-coded, but I mean, this is experimental code anyway. And this is where I'm going to be saving like arg, right? I'm taking the stack, right? I know that it's fresh. I know that its current state is like this, right? And I'm just basically like patching the stack. I'm patching the stack and I'm inserting that arg in there. This is pretty cool. This is pretty interesting, I think. Yeah. It's one way to do that, I guess. It's one way to do that. But it's kind of like sad that now I can't really pass a value in here, especially if I do something like this, right? So generate a create. I'll need to think how I backport this functionality to the previous example and stuff like that, so I can use for each again. Right. So anyway, let me try to do this kind of thing. So what do we have in here? So it complains about arg, and this is because the compiler cannot see that we're actually using this thing in here. All right, so this is rdx. All right, so now I'm gonna go in here. Generator restore the context. It can't see this entire thing. Maybe I need to bring that thing in here, so a little bit higher, so we can put it somewhere here. Okay, generate a create. Okay, so here we're not creating anything. Okay, let me temporarily kind of get rid of this entire thing. So I'm gonna just take the A and I'm gonna pass it in here. So we were just... So this is Fibonacci. No, it's not Fibonacci, it's actually squaring. It just worked, but I mean, I haven't finished fixing all of the warnings and it already fucking worked. Okay, so all right, it worked, but I didn't finish fixing the warnings. So I probably have to do... That's kind of cool, right? So this is kind of cool. So this is, it doesn't like it because it's a void star, it has to be void star, and what do we have in here? I have to, you know, cast it back. Okay, so now if I just run it, it works. Right, so essentially it distinguishes between first call and consequent call, and depending on what kind of call you do, it either returns the value of the next through this argument or through the return of the yield. This is kind of cool, and since it's infinite, I can actually infinitely extend this loop like as many times as long as I want. Right, so this is kind of cool. Right, so this is an ability to send value into the generator. Right, so you can not only receive values out of the generator, but you can send this value into the generator through the yield. So this is sort of like a switching points between these two things to communicate with each other. This is kind of cool. This is kind of cool. Right, so and how do I backport it to this example where we did Fibonacci, right? So because through that argument, we were passing very important information, I believe. We were passing information about the upper bound, right? So because this is the upper bound, I don't really know, right? So if I just try to run this entire thing, I don't think it is going to work, right? So because there's no, you can't pass this kind of argument in here. You can't really pass this kind of argument. And now I have to pass this kind of thing, but if I pass null in here, the first ever thing is going to, yeah, it's going to return null. Like, how do I do it now? So for each is not really usable anymore, as far as I can tell. Right, so the way I can iterate this entire thing is by doing generator next G, and I provide the upper bound like this. I want 1,000,000, and I get a value out of it, right? So which is going to be just like a long, and I can print that value, something like this. So I'm just printing that value. So this is going to be the first value that we've got. And then I probably just need to keep polling this entire stuff, right? So I'm just checking. While it's not dead, I keep repeating this entire stuff. And that way I will poll, and then it returned null to me for whatever freaking reason. So I suppose this is because I have to do it like that. If it becomes dead, I have to break out of that. Yeah, so it kind of broke the entire beautiful for each macro like this, which I'm not really a huge fan of. Or did it break it actually? It's kind of difficult to tell. So, and by the way, here, since those are consequent polls, we don't have to pass anything in here. We can just keep it null. But did it actually broke? That's a good question, honestly. Did it actually broke it? Because I feel like I can still I feel like I can still do something like this, where I can just do stuff like that. Then, while this thing is not dead, keep polling this entire thing. But we're polling it now. Can you see that shit? with the null. Right, we're polling it with the null. Right, and then I can simply print the whole stuff. It's just like now the value that I passed in here, I have to pass it through the first next. Right, is that a good... I guess it is. This is how we do it now. I guess that's how we do it now. So that means maybe the way we can kind of fix the beautiful macro is by providing the initial arg, which then we can pass in here. Right, that's one way to do that, and that initial arg is obviously going to be this thing. Right, so I'm gonna put it in here. Right, so that's kind of the, yeah, I guess. So that's kind of the macro. So you pass this value in there, and it just like uses this kind of value. Or we can always pass this value no matter what. Right, so because our generator never gonna use the result of yield anyway, so it doesn't really care. So we can just like always pass it in there. In any case, now we have an ability to send some data into the generator, so our generator is kind of complete, sort of. Right, so that's kind of cool. So I will see how I can use these kind of generators in my projects. It's obviously kind of similar to the coroutines I developed, but it's different. Right, it's kind of different. So I think it's useful for different use cases. In any case, that's basically it. Thanks everyone for watching, and I see you all on the next recreational programming session with Mr. Azozin as usual. Love you. Mwah.